All right, good morning. Make sure we're doing what we think we're doing here. Just get one of me, that's probably sufficient. Oh no, that's the infinite me. There we go. Okay. Okay, great. Good morning. All right, the goal is to be live at 10:15, but technology is always a little bit of a challenge, as we know. We are three audiences this morning. We are here in Santa Barbara, of course. We are also remote Westmont College as well. Westmont College here in Santa Barbara. We are also Westmont College around the world right now. We had our first check-in from one of our students that is in South Africa and other places, so that's kind of cool. This is, of course, the Mayterm course. This is our seminar, part of our 5-week class. Today's lecture is scheduled for 2 hours. Students that are part of Westmont can communicate over the Slack channel that we've got going on. And hopefully I'm small again now and I'm not taking up the whole screen. And today we're going to do a little bit more introduction for Java as we continue learning about the Java programming language in an effort to learn about more general ways of thinking about computer science. So let's just arrive for a second. I know that I'm always getting ready for class and just want to make sure that we are aware and conscious of being here. So let's make sure that we've turned off our notifications and just remind ourselves that we are responsible for maintaining our own attention. All of these devices, Facebook and notification, would love to steal all of our attention, but it's very important that we take control over our environment and architect an environment in which we are able to have agency about what's happening. In the same way that if you are a recovering alcoholic, you don't put a bunch of alcohol in your house. It's because willpower only goes so far, right? You've got to change your environment in order to be who you want to be. So that's for our notifications. I was thinking this morning about just blessings and the fact that I've heard many people, pastors primarily, just talk about the fact that we are blessed to be a blessing. So you can think about why it is that someone might be rich or why it is that someone might be born in another place. We're in Santa Barbara. We have a lot of resources available to us, and we have a unique responsibility to take that, bless others. We're blessed to be a blessing. So let's remember that as we launch today. Any comments or anything we need to address before we get going? Great. All right, let's do it. So the first thing, let's just orient ourselves to the overall circumstances in which our programs are running. This is pretty basic, but it's important that we have these basics down. And if you have any misconceptions about the way some of these basic components work, then we should talk about them, but so that we don't build up a mental model that's incorrect. We want to have a correct or effective model of what the computer is doing, so that as we try and debug the computer, as we try and build our systems, we are working with it in a way that is accurate. So we know that computers are programmed to perform many different tasks. That is specifically a kind of computer called a general purpose computer. And so the folks here in the room are mostly on laptops. Looks like everyone's on a laptop. Laptops are sort of the current most common example of a general purpose computer. There are lots of computers in our world that are not general purpose computers. For example, the computer that's in your microwave. That microwave definitely has a computer that manages things like turning on and off the power and managing a clock and a couple other things. You can't play Super Mario Brothers on your microwave, at least most microwaves. And so that's an example of a specific, a one application computer. The computers in your car are typically just a specific application. But the computers that we program typically are general purpose computers, and that means that they can run many different kinds of programs besides just sort of a specific program that it's made to do. So what is that program? Even one-purpose computers have a program. They tend not to be very flexible. They tend to be in the chips themselves. But general-purpose computers have programs that can be swapped in and out. They can run different programs at different times. And the program itself is just a sequence of very, very basic instructions. So it's a collection of all the little things that a computer can possibly do, put together in a particular order to achieve some kind of effect. Like you can imagine that each one of the pixels on your screen can be turned a different color. And so those are the basic instructions, turning the pixels on and off, but we build them up to create things like showing images and animations and interactive user interfaces, things like that. So the computer executes these very basic instructions very quickly. That instruction might be collect some input from the user. Could you please get me a character from the user? Could you please get me a touch from the user on the touch screen? Maybe one of those commands is showing output to the user. Let's write a character to the screen, to the console. Let's show a clown emoji in our instant messaging app. Hey, anyone use any? Oh, no, it hasn't come out yet. We've got a whole new set of emojis coming out in June 2008, right? June, I think. I'm super looking forward to the new microbe emoji. That's one of them that's coming out. I don't remember off the top of my head any of the other ones. I was so excited about that. I think there's a kangaroo. That might be new too. So one of your instructions might be to write one of these emojis out. And maybe it's a new one that's coming out very shortly. You might want to manipulate data, right? You might want to take some data. You might want to add it. You might want to subtract it, something like that. You also might want to make a decision about data. And that decision is really at the heart of what makes general purpose computers powerful, because they can make decisions based on what they see in the world or what the user has typed in or what they have calculated. And based on the results of that, they can take one course of action or another course of action. And by chaining together those decisions in a lot of clever ways, you get things that appear to be very powerful, that are very powerful, by running lots of little instructions quickly. So what we're learning is we're learning a skill, the skill of programming, which is putting those different small instructions together in a way that helps us to achieve whatever it is we want to make. And I talk a lot about how we can use this skill to do good things in the world. It is very much a skill at some level. It's also a way of thinking. But the skill part, the stuff that we're learning right now, is very low level, right? I sometimes use the metaphor of the bricks in the cathedral. Probably heard me say this one before. Learning to program is like learning to lay bricks, but the reason why we program is not to lay bricks. The reason is to build buildings, to build hospitals and cathedrals and schools. Same thing with programming. The reason we program is not because we love the syntax of Java or we love typing semicolons in. It's because we want to use those instructions to do something bigger. And so both the skill of learning how to program, but also thinking about where you're going and the something bigger, are two things that you have to keep in your head at the same time, because both of them dictate the other. They both drive decisions about where you're going and how you're getting there along the way. One of the arguments for why a liberal arts education is an important part of computer science education, because you need to know where you're going. Okay, so that's programming. That's what we're doing when we design a program, when we implement the computer program. We also think about the computer in different chunks. We think about the physical computer and the peripheral devices. We call those hardware. Those are the pieces that you can touch, that you can manufacture with physical materials. The other piece that we've got that's part of program is called the software. And the software is the piece that we develop with intellectual ability. This is the instructions, but it's like a book, in that a book isn't really is partially a physical thing. It's partially pages, but it's also the story that's being told in the book itself. And so if you think about the story in a book, that's like software. But if you think about the pages of the book, that's like the hardware. So we've got that same breakdown in our world with computers. We think about it as hardware, the physical components, and software, which is the program that gets executed. They can be decoupled in certain ways, so we think about those things in categories. And parts of the hardware, any general purpose computer is going to have all of these different components. It's going to have a CPU. You might have heard that abbreviation used before. That stands for Central Processing Unit. When I was growing up with computers, people thought a lot about central processing units, about the CPU, because in my maybe high school, early college days, the CPU power was growing really quickly. And so when you went to go and buy a computer, you were thinking a lot about which chip you were going to have, because the chip speeds and the chip capacities were growing. Every few months you'd see a new version come out. 386, 486, Pentium. The speeds were going up from megahertz to gigahertz. And so you were always thinking about how much do I want to pay for the cutting edge size of the chip. Nowadays, the chip is still something that people look at, but it's less important. We find that we are more interested in the entire collection of hardware that we're buying at one time. So the chip is important, but we also care about the screen, and we care about the resolution of the screen, and we care about what the keyboard's like, and we care about the form factor, and some of us care about the aesthetics of the computer as well. That will cause us to pay a premium for certain brands, which will not be named. It's more than just the CPU, right? So the CPU is the chip. It's the brain of the computer. It's sometimes called that. It is the part that's responsible for executing those little instructions. It's like the train switch that is sending data at different places, that's picking the instructions to run next, and that's actually doing the work of it as well. Now we also have data storage. Data storage, we think of, this is a little bit of a model in that it's not exactly the way reality works, but it's pretty close. We think about data storage as having a primary component and a secondary component. The primary component is memory, or RAM. RAM stands for random access memory. These are also implemented in chips, but it's a different chip than the CPU. And depending on how much RAM you have, your computer can have more programs running at once, more quickly. And RAM is very quick compared to the secondary storage, which is your hard disk. Traditionally, this was a spinning platter, a physical spinning platter. Increasingly, with our smartphones and our laptops, those spinning platters are being replaced with solid-state drives, which are actually not that different than RAM. They tend to be a little bit slower, and you tend to get a lot more of it. The benefits of it are that it doesn't break if you drop your computer, in the way that a hard disk, because it's a mechanical device, tends to have mechanical failures. Solid-state disks don't have that. Solid-state disks, however, are more expensive. So there's a trade-off between them. But we call them both secondary storage, not because of the physical way in which they're created. One is a mechanical disk, the other is chips. It's not about the physicalness of it. It's more about the role that it plays in the computer, and that role is dictated by the speed. Both of them, whether you have a hard disk or a solid-state disk, are going to look like a disk on your computer. So if you open a file explorer, you open the Finder, depending on your operating system, you'll see your hard disk has a bunch of files and folders in it, regardless of whether it's implemented as a mechanical spinning platter or as solid-state chips along the way. Okay, that's within your computer. Now you also have peripherals. So peripherals in a desktop computer are things like monitors and keyboards. They're very separate from the body of the computer. Of course, as we're using laptops and smartphones, it tends to be that these peripherals are all bundled together in one big package. But you can also, and even in laptops, you'll have things like an external DVD drive or maybe a flash drive, which acts like external storage as well. And then, of course, modern computers would be nothing without a network. So a network is critical for doing any sort of connection between computers, sharing files, or communicating with each other via the internet, largely. All right, so just some pictures of what we got here. There are a couple images of what these devices look like. On the left is a chip. I'm not 100% sure what version of chip this is, but what you see is you see a whole bunch of little pins on the top of that. All that texture are actually individual wires that are coming out of the chip in order to connect that chip with the rest of the computer. So let me see if I can draw on it. So what I'm talking about is this, and those little pins there are that bit right there, all this in here that goes around. That's connecting the chip with the rest of the world. For example, the memory. That's how memory comes in and out. That's the way messages from the internet come in and out. It connects to other pieces on the computer as well. On the left here, we've got two hard drives. They're both hard drives. One's got the cover taken off. And you can see that this is the older style where you have the actual platter that spins around. And this one right here also has a platter. It's just enclosed in a case, so you can't see what it looks like. If you're familiar with record players, it's sort of a similar mechanical style of reading. This arm goes back and forth in order to cover the entire width of the disk there and read information off that mechanical disk. That disk spins, typical spin rates are like 5,600 revolutions per minute or 7,200 revolutions per minute. The faster it spins, the more information you can get at a given time. Now that's a desktop computer, but what about our phones? So this is a screen. This is a photo from a website that's showing you how to replace a battery on a phone. I believe it's an iPhone. And what you can see here is you can see that inside a phone, the majority of the guts of the phone are actually taken up by the battery. The battery, here's a replacement battery, but the actual battery is right here. And the largest part of the volume of the phone is that battery. It's the thing that requires the most space. It stores the energy. It's in some ways the most critical part of the phone because you've got to keep it running as long as possible. And then all around the edge, you see those same components that were in our desktop computer. You'll have a CPU. It might be actually underneath the battery. I'm not sure where the CPU is on this particular model. But you have input-output. You have things for connecting to the internet. You have controllers for the speaker and for the proximity sensor. And so all the components of a normal computer are sort of wedged in around the battery. And part of the reason why a battery on an iPad or a tablet lasts so much longer is you just have so much more space. And of course, on this side, you have some components too. That's where the screen is located, on the other side of that fold-out part. All right, so now if we connect all these pieces, let's see if we can come up with a model. I'm going to try and draw this. The way these pieces connect in a computer is through something called a bus. And the computer bus is actually just a sequence of lines, of wires, that transmit information between different places. So a bus is like a road. Many different cars go on that road, and the cars are like information, and those cars are going to different places. One of the places that they might be going is they might be going to we'll call it the ports. Let's see if I can write on here so you can see it. Ports. This is going to connect to the bus. In addition to the bus, you're going to have the CPU, or the main brain of the computer. That's going to be connected to the bus as well, and that's going to be for dictating where all this information flow goes. Also on the bus, you have main memory. So this is your RAM. So if the CPU wants to get something or store something, it'll send information out on the bus, and it'll get stored in RAM. On the other side, I mean, the side doesn't matter so much, but you also have a component over here, which is the disk controller. Disk controller. Abbreviate that. And connected to that are your hard drives, or your solid state drive, your secondary storage. So information can be moved from your disk drive to your RAM, and then from your RAM to the CPU if you need it to. And then finally, the other thing that we want to draw in this model is a network controller. And that network controller is responsible for sending things out to the greater internet. An I for internet. Now all these things are within the body of the computer. So if I draw a big boundary box around here, that's sort of the boundary of the computer, the actual physical bounds of the computer. So all of the peripherals for a traditional desktop computer then get linked off of the ports. So you'll have your printer, you'll have your keyboard, you'll have maybe a monitor, or you'll have a microphone. All these things are the input-output components that are coming out of the ports, things that you plug in, your USB drive, your VGA spot, all those kinds of things as well. So your mental model should be something like that. It should be componentized in that way. And so the question then that I have for you guys, or I guess anyone on Slack who can answer fast enough, is where is the software actually stored? When you write software, where is that stored? It gets run in the CPU, so it's definitely stored there when the program is running. Usually the CPU just holds a few of the commands that are running at one time because it doesn't have enough memory to hold the whole program. So there's a natural fallback. If it's not in the CPU, it's probably in the RAM, main memory. If it doesn't fit in the main memory, it's probably in the hard drive, right? So for long term, your program is a file usually. And so that file is stored on the hard drive. When it comes time to run the program, it's moved from the hard drive into your main memory. And then the CPU picks out instructions a few at a time from the RAM in order to run it. So if the question is, where's the software stored? Well, it's a little bit of a trick question. It depends exactly what you mean by when is it being stored. So for long-term storage, it's going to be in your hard drive. And when it's being run, it's in your RAM. And when it's being readied to be run, it's in your RAM. when it's actually being executed, it gets moved into your CPU as well. And of course, if you send a program to someone else, I guess it's on the internet. It could be on Dropbox too, right? Sort of an extension of your network model. What about, how does this compare to a smartphone? So this is a great example of how we think about a desktop computer, but what is a smartphone doing that's a little bit different than this? So one observation is you don't have ports, but also you do have ports. How does that get resolved? Right, different input through the touchscreen. So what happens in a smartphone is conceptually the ports are still there, but from a user perspective, you don't see them. So you don't spend a lot of time plugging things into and out of a smartphone. Sometimes you do for a single peripheral. But there's still, within the architecture of the smartphone, these components are all still there. There's still an idea of a port, but that screen and that touch screen, there's usually not a keyboard, but they're all, what we would do is on the smartphone, we might do something like take the boundaries of the computer and actually extend it to include a bunch of those peripherals as well. But just because they're included within the physical part of the smartphone doesn't mean that there aren't still connected architecturally as a port. Any other thoughts about this? Let's see. Does it matter which operating system you use for this architecture? At this level, no. At this level, most operating systems all have an architecture that looks something like this. Part of the architecture that I've drawn here is dictated by the operating system, but part of it is also dictated by the chip. The chip and the operating system. The operating system is a special kind of software that runs other software. They work together to create a model. For the most part, all computers have a architecture that looks something like this at this level. When you start to get more into the details, it tends to get a little bit more difference. Okay. All right, historically, though, it hasn't always been like this. Our computers have looked a lot different over time. So here's an example of the ENIAC computer. It was one of the early computers that was developed. ENIAC, just learned this pretty recently, actually was an acronym that stood for the Electronic Numerical Integrator and Calculator. It was an example. I think that person in the picture there is in a military uniform. It was certainly the case that early computers were used for computing ballistics tables for artillery applications of trying to launch shells, mortar shells usually, and trying to figure out where they were going to land based on the position and velocity and weight, the position and velocity with which they were launched. And so the first computers were used to compute a bunch of tables for doing these kinds of things. They were computing the tables, and they took up whole rooms like this. This is, if you remember back to our slide from the last class where we had the humans and the bacteria and stuff like that. This is way down low, about at par with what humans were doing. But as you can see in that picture, there's a lot of manual connecting those wires together. Those wires that you see eventually became the bus on the computer. And the switching that happens on modern computers, where like the CPU will send information to the RAM, and that's now done in software. But originally, if you wanted to move stuff around, you had to like go and plug in all those wires to different locations, as if you were an old school telephone operator trying to connect people to long distance and such. And these things also took a lot of electricity. Some of the early computers, when they would turn on, would cause their entire city's lights to dim because the amount of electricity that they took. That was usually when the decision making was being done by vacuum tubes rather than transistors, but still. Another picture of that early computer, a little bit posed, I think, but some of the early computers were women, of course, and here they are learning a new skill, not doing the math anymore, but managing the computers that do the math, and they're acting like the bus right now, trying to write programs and change the architecture of the system so that specific programs will run on those. All right, Java in particular is one way in which we can write software for our computer. It is, we mentioned last class that it's safe and portable. Different people would argue about whether or not it's safe. It is safe in one particular way. It's designed to be safe, so it's a good start. It's portable. Portable is an interesting attribute of the language because many different languages and frameworks try and run on multiple different platforms. Java is pretty good at it. And what I mean by that is if you write a program in Java, you can often run it on many different computers. And that's not necessarily true for many other languages. But Java programs run pretty easily on different platforms. And so we say it's portable. You can move code from one place to another. And we also say it's platform independent. And the reason why it's platform independent is because it never gets translated into machine-specific code until the last minute. So obviously every chip is going to have unique features to it, but Java doesn't actually get translated into that unique chip language until the very last minute when it's run. Java has tons of libraries for encryption and for communication on the internet, libraries for, all kinds of things. Math and high-performance computing and machine learning, all kinds of stuff. It's designed for the internet, and it also is the primary language for Android phones. If any of you are interested in developing smartphone applications, Android programs are usually written in Java, as well as, of course, being able to run Java on laptops and desktop computers as well. As long as we're talking about history, Java has a history that goes back to about 1996 when the first version was released. The most important thing here that I want you to get are two things. One is the history of Java, that it started in 1996, so quite a while ago. That was the first version. And the other thing I want you to see is the naming change or the versioning change, because that messes up a lot of people as they're trying to just work with the libraries and stuff. So what you can see is in 2004, there was this shift in numbering from saying that we're going from 1 point something, 1 point something, 1 point something, until 1.5, at which point we started saying we were using Java 1.5 and we were using Java 5. And both of those things meant the same thing, but it was very confusing because it looked like there were two completely different numbers describing the version of the Java language that you were using. To make it even more complicated, you can see that just recently Java 1.10 was released. And if you didn't understand the versioning scheme, you might think that those are they're like floating point numbers. You might think that that is 1.10, which it's not. Because 1.10 as a floating point number would be the same as 1.1, which was released back in 1997. See what I'm saying? Like if you treat them like floating points, the version in 1997 and the version 2018 would be the same. This isn't a floating point number. This is a versioning scheme that I've heard described as SEMVAR, semantic versioning. And what it means is you have a 1, that's the major version, a dot, and then the next thing is an independent number, which is a minor version. So that 10 is a 10. It's not a 1.0. Yeah, Tim. Are they going to make 2.0? That's a great question. I haven't heard anyone talking about that, but I think one of the reasons why it went from 1.4 to 5 is because the idea that you were going from 1.3 to 1.4 suggested that you weren't making big changes to the language, you're making minor changes, but in fact there were some large changes that were happening. So I think the switch from going from 1.5, 1.6 to going to 5 to 6 was more along the lines of jumping over 2, 3, and 4. So I think that's what's going on. Well, you know what? We are going to talk about them. We are going to talk about them, but we're not going to talk about them in a historical context. So we're not going to talk about them as there was this, and then there was this, and then there was this. We're going to talk about it more. We're going to talk about these features more as they come up in just writing new programs. So we are going to talk about, for example, generic classes, and we are going to talk about the enhanced for loop, a little bit about streams. Some of them are more important than others. And also, this list of features isn't complete. So there's a bunch of things that are hidden there that we'll talk about as well. Okay, so we were working last class with Eclipse. Eclipse is an example of an IDE, or an integrated development environment. It is many things, but one of the things is an editor. So it enables you to type text. It is designed not for typing like an essay, an English essay. It has the support for writing computer code. And so it gives you the ability to write and modify source code in particular. And then in addition to doing that, it's actually kind of like this, not the composer. What's the person in an orchestra who stands at the front? The conductor. The IDE is a bit like a conductor, because what the IDE is doing is it's letting you write a little bit, but it's also calling the compiler while you're doing that, plus it's interacting with the internet, plus it's collecting output from a bunch of programs. So it's actually kind of an umbrella for a lot of things that are happening, and trying to present to you a user interface that is clean and consistent with all the different underlying processes that are happening. They also have collaboration tools, so you can interact with other people through the IDE as well. It also presents a user interface for debugging that code, and debugging is a skill that students really resist learning for some reason, but it is the best way to solve problems. And I mean like specifically the tools within the IDE for debugging. Other IDEs that you guys have used? PyCharm, yeah, Anaconda. Well, Anaconda comes with an IDE. Usually the one in Anaconda is Spider. PyCharm is for Python. Spider's for Python. What about iOS? What do we use in iOS? Xcode. So Xcode is the IDE for iOS. Eclipse is open source. Android Studio is one that's used for Android. There are some commercial companies that make them as well. Microsoft, of course, has Visual Studio. So there are quite a few of them. Okay. When you program in Java, you have to be aware that Java is case sensitive. All right, so a lowercase letter and an uppercase letter are not going to be interpreted the same by the language. Java, unlike Python, doesn't care about your indentations either. People care about the indentations. We want to see indentations that help us read the code better, but the compiling of the program doesn't matter. The indentations don't matter like they matter critically in Python. We have two things that happen when we write Java code. One is that we compile it and we translate source code into these class files. And the class files are the things that are platform independent. We'll look at that in more detail in a second. And the class files contain those lowest level instructions that get translated by the Java virtual machine into hardware specific instructions. So what I want to do now is I want to shift gears a little bit, and I want to go back to that Eclipse, the process we were going through in Eclipse of writing a Hello World program. And I'm going to walk through it in Eclipse while you guys watch, I guess. And as we shift gears, remember the reason why we're doing this is to prepare to turn in a Hello World program for our first assignment. And then, of course, we're going to be writing other programs in the future. So this is just to get us launched. Shifting gears, anyone? Any issues raised? Anything from our remote folks? Okay, so here we go. Let's shift over to Eclipse. All right, so I've started Eclipse. We have a remote session. Started Eclipse. We have nothing in my world here. So the first thing that we need to do when we start a new project is we have to actually create a project within our workspace. So the way I'm going to do that is I'm going to come over here to my Package Explorer. I can either right-click here and go under New, or I can go under File and find that same new menu as well. I'll right-click in my Package Explorer and go New, and I want to create a new project. Java project is a shortcut. I'm going to show you what would happen if you did it the longer way. I'm going to create a new project. I get this complicated wizard, and this wizard is going to show me a whole bunch of different kinds of projects that I could create. What's the difference between these different projects? They're templates for different kinds of projects, and they tend to have different ways in which they support, like Java FX, for example, comes with a bunch of libraries that are going to help support user interfaces. Maven is a kind of project that's particularly internet aware when you want to use a lot of libraries. Gradle is an alternative way of building your project. General is if you don't want to commit to anything, you just want a project. What we're going to do is we're going to create a Java project, just right there. That would have been our shortcut if we had taken it from the menu. All the ones that I recognize here are all Java frameworks. So the question is, are all these Java frameworks? All the ones that I recognize here are Java programs. Eclipse isn't specifically for Java, though. Eclipse is an IDE that can work with many different languages. So if you download the right toolkits for Eclipse, you can have C projects and web projects. And I've seen C and I've seen HTML, CSS projects. I've seen Hadoop projects, which are a kind of Java project, but they're for big data computation. And so just to repeat the question, why is there no universal IDE? It's not that it's not technically possible. Eclipse certainly strives to be that. So Eclipse is open source and enables people to create plugins so that they can add their own things to it. But I think what happens is you get competing preferences. So some people don't like the way Eclipse looks or the way it's architected. Some people, sometimes there are business interests that are involved as well. For example, Apple uses Xcode as their environment because they have a particular business interest in making sure that the tools for building apps in the iOS ecosystem are well supported. So they don't want to rely on some third party to make this tool for developers. They want to make sure that the tool for their developers are as good as it can possibly be so that their apps end up being as good as it can possibly be. So there's a business interest there. There's this little bit of a security interest in the Apple case because their IDE does encryption on the apps, and they want their apps to make sure that they're tightly encrypted so you don't get, as much as possible, you don't get malware in your ecosystem. And so, for example, Eclipse was used for making Android projects for a long time, and then Google decided to support Android Studio. Android Studio and Eclipse seem very similar. I'm not quite sure why there was a shift because Android Studio isn't open source the way Eclipse is open source. But the biggest thing I noticed is that just the interface was just a little smoother for whatever reason. I think you can do Python in Eclipse. Yeah, yeah. I think you just have to get the right plugins for it. Okay, so let's keep going here and make our project. I'm going to hit next, and that's going to take me to the next location. A lot of options here that we can look at. For now, we don't have to work with very many of them. But what I'm going to do is I'm going to name my project Hello World. I think at this level, so I could have spaces. This default location says where on my hard drive am I going to put this file. And this has already, the default location means you're going to put it somewhere in the workspace you've already chosen when you first made it. I have the option here of selecting which version of Java I want to write code for. I'm going to go ahead and choose 1.8. I could, the syntax that I use most often, 1.8, 1.9, and 1.10 are about the same. There was some notable changes between 1.7 and 1.8. All of them at the level that we're doing our coding in this class. Anything probably 1.7 and up is going to be fine. You may not see as many in your computer. So when you hit that drop-down list, you may not see all those different options because you might not have those Java development kits installed on your computer, and that's okay. You don't need to have them all. So we'll go ahead and hit next. And you can see some information about the project setup. These are information about where we're going to keep our source code in our project, information about other projects that our project relies on, any libraries that we want in our program. The most important one here is you need some kind of runtime environment. These are all the default functions and classes that you need to run in Java. Because they're so essential, when you build a project, this automatically gets included with your project as well. So we can just hit finish. And now over on the left, you can see that a Java project has been created. You can open up that system library if you want to see all the different libraries, not necessary. And then here is a source folder, which is where we're going to put our code. So I'm going to start, and I'm going to show you the very manual and tedious way of making a Hello World program. And then what we're going to do is I'm going to show you the Eclipse way, or the faster way to do it. Okay? So the first thing that we would need to do in order to create a Hello World program is we need a new file. In Java, files and classes are tightly linked. You have one public class for each file. Right? So I'm going to use the same new mechanism, but instead of creating a new project, now I'm going to go down here and make a new file. Where am I going to put it? Well, I'm going to put it in my source directory of my project, and it's giving me an error that says the name cannot be empty, and that's because I have to give the file a file name. We'll go ahead and call it hello world.java. And you can see that it has created something called the default package, which we haven't talked about yet. And here's my file. So this file is now visible on my hard drive. If I wanted to go look at it, I would have a file that has no contents in it. You can see that Eclipse also did the work of opening it up for me in the center. I'm just going to close it for a second by hitting the X there. And now I can double click on it to reopen it. And now I have an empty file into which I can write my code. In Java, it is an object-oriented language. So everything exists within objects. So I'm going to make up my first object here. I'm going to go ahead and say public class hello world. This is going to create my object. And I'm going to put some curly brackets there. Curly brackets take the place of indentation in Python. So curly brackets define a scope. It is, when you put curly brackets around something, it's like indenting. Everything inside it, you usually indent it just for visual effect, but what's important are that the curly brackets indicate what's inside. So I've just defined my class, and what I'm going to do now is create a method. I'm going to create a method. I'm going to use this public keyword we don't know yet. I'm going to use a static keyword we don't know yet. I'm going to use a word we don't know yet, void, and I'm going to call the method main. I'm going to give it some parameters, a string, which we haven't talked about yet, an array of strings. I'm going to call it args. And now within the body of my method, I'm going to do this command, system.out.println hello world. All right. Now, this is about the simplest program that you can write in Java. I'm going to save the program by hitting my little one of these two icons, save all. Now when I want to run this program, what I do is this button will do run as well, but I always like to come over here and run it from the file to make sure because you can have multiple runnable programs open in your package in your workspace at one time, I like to be very specific about which one I'm running. And so I'll pick the project, I'll go down this list to run as, and then run it as a Java application. And you can see down here on the bottom that hello world just got written out just to prove that wasn't some sort of cooking show, pre-cooked pie that wasn't actually made on the set. We'll do that and just run it again so that you can see how the change actually affects the output. It's asking me if I want to save my files first. I do. And so you can see it's being output down there at the console. All right, so let's see. That was a very manual way of writing that class. That's not really the Eclipse way of doing it. Right? The Eclipse way of doing it is to have the computer write as much of the template code as you possibly can. So I'm going to delete that class and show you how to do it much quicker. I'm going to right-click and delete. It's going to ask me, do I really want to do that? Yep. And now what I'm going to do is I'm going to highlight the source package, and I'm going to go back to my new command, and I'm going to ask it to make a new class for me. That's what I just did manually. And now it's going to give me this wizard that's going to fill in the template for everything I just made. So I want to name my class hello world, and I want to check off this button here that I would like a main function in it as well. It's giving me a warning to not use the default package. So if I was going to get rid of that warning, I could put something in here. A reverse URL works fine. It's just some text to describe a file hierarchy. Then I'll finish it, and you can say, bam, it writes all the code for me. It has even put a little to-do marker there on line 6 telling me that, oh, this was automatically generated. You need to make sure you put some code in here you want. So I'll go ahead and add that code that I just had. I will delete the line above it. I will run it as a Java application. All right. So what I did is I really leveraged Eclipse in order to write as much of that as possible. The one thing that's missing from this that I would want you to make sure that you do before you ever turn something like this in is to put some comments in here. So comments in Java start with a slash and a star. And if you do 2 stars, it'll do a templated comment for you called JavaDoc. And then you can write some sort of comment that describes what's going on. What's important here in terms of the comment is this slash star at the beginning and this star slash at the end. That's a block comment. Save it. I could run it again. Okay, so let's see. I'm going to call a little bit of an audible here in terms of the lecture. I hadn't intended quite yet to break and write this program, but I feel just based on how things are going right now that a good thing to do would be to pause and give you guys a chance to just do what I just did, and then we can come back and describe the different components of this program. Why don't we take 10 minutes? Let's come back at 11:20, so 9 minutes, and we will pick up and describe a little bit the specifics of what we see. Does that sound all right? Any questions before we cut off for a few minutes? Okay, let's pause, and we will be back in 9 minutes for the folks that are watching online. See you in a few seconds. And again, what we're doing is we're writing a Hello World program, and we can turn this in if we want to. Okay, audio back on, and we're getting our screen back. Boom, hello, and then here I am. Hello. Okay, great. Okay, so we were just working on our Eclipse Hello World. We had a comment on our YouTube feed that was pretty good. The question was, who invented Java? And that's a tip. That is a good question. It is a question that gets answered a lot for other languages more so than Java. Python, for example, has a provenance or an originator that was very clear. And sometimes other languages have similar origins. Java, I don't know exactly, but I know that very early on, Java was very much part of the academic programming languages community. So it very quickly, I'm not sure who was exactly the person that originated it. James Gosling is probably what we're getting online. So I don't know the story of the origin of Java, but I know that it was very quickly adopted by the academic research community, in particular the programming languages researchers. And because of that, there's kind of a very concise and precise syntax for Java that's consistent throughout the whole language. Because I'm kind of OCD, I like that. So one of the reasons why I really like Java as well. It is the intellectual property belongs to Oracle, the corporation. So in as much as it may have originated, actually now that I think about it, I think that the originator was a employee of Oracle when it started, but we can double check that. Okay, so what we were just doing during our break was we created a project within our Hello World. Yep, got a confirmation that the originator was at Oracle. We were creating a project. We did that. That was good. We created a file. We showed two ways of doing that. One was manually by creating a file as a file and then trying to write the code ourselves. Another way was to create a class. And when you create a class, a file is also made as well. One of the things that we ran into here in person in terms of the way in which the classes work is that the class that you're writing, the software that you're writing, and the file that it's saved in has to be very specifically tied. So the name of your class, which should start with a capital letter, so like Hello World, that has to be stored in a file called helloworld.java, where Hello World has to match exactly, but the .java is only in the file name. That's just something about Java where those things are paired very specifically together. Now, if you're familiar with other languages like Python, you know that you don't have to have objects in order to run commands or run a program. In Java, everything happens within the context of an object. There's no such thing in Java as code that is outside of an object. And so even when we want to write a program that doesn't even need objects, we still have to create an object and put that code inside it, like we did for Hello World. That Hello World just printed something out to the console. We didn't use instance variables. We didn't really use methods. We didn't use any of the power of an object, inheritance, or anything like that. But we had to put the code within an object because the way Java works is very strictly through objects. It's part of the OCD-ness of it that I like. We also saw the difference between writing the code manually by typing it out ourselves and then writing the code using the Eclipse template and wizarding tools. Really, I encourage you to get to know the Eclipse hotkeys for doing these kinds of things. It makes the code so much faster. And when you learn about refactoring, Eclipse will restructure your program for you automatically as well, which is really great. In terms of this class, though, when you guys turn in your code, there's a couple things that I would like to see. I would like to see, first of all, that everything that you turn in has comments on it. That's an important part of communicating to other programmers what your intentions are in your code, but also an important part of communicating to yourself 6 months from now when you open your code again and you have no idea what you were thinking 6 months ago. The comments are even helpful for you to understand what it was that you were writing. I also want you to go through and clean it up. So I would like spelling errors removed, even though spelling errors are okay as long as they're consistent spelling errors. I'd like the things to be spelled correctly. I'd also like the indentation to be done correctly. So here's a little trick for you. Let's take a look at one of the Eclipse tricks that we can use. We'll switch over to Eclipse real quick. One of the questions that Lisa asked here in class is if we wanted to print two things, could we just put another print line there? The answer is yes, we can. So if we do that, spelling it right after I just made my big spelling spiel, and we decide to run it as a Java program, we'll see both of those things printed out to the command line. You can also see that everything's pretty well indented. But let's say let's see I was using really bad indenting practices. I did something like this, and let's see, let's say I had them all in one line like that, and then I had 2 there, and what a mess. And I decided to put, decided to put a lot of space there. Okay, so this is valid Java code because indentation doesn't matter. All that matters is the curly braces, and the end of a line is dictated by the semicolon, not by the fact that it's a new line. So it's completely valid Java code, but it's really a pain to read. So what you can do is Eclipse comes with these formatting tools where you can just come under source, which means all the commands that modify your source code, and hit format. And it'll rewrite your code with all the indentations really nicely lined up. And that helps visually to have the curly brackets and the indentation match up, even though it's not strictly necessary. It's also possible to just format a piece of your code. So if you just want to format that method, for example, you can go under source and just say format element, and it'll only clean up the current scope block that you're in. So when you turn something in, I would like it to be properly formatted. I would like any sort of auto-generated code to be removed from your class, and I would like everything to be commented. And your code, all your code, somewhere at the top should have an author that I can understand. So Eclipse put in DJP3 because that's my username on my computer, but I would like you to write out your name here, something like that. In addition to that, if you end up turning in code in pairs, because in this class you can work in a pair to turn in your code if you'd like, if you do that, only one of you should turn in the source code, and both of your names should be at the top. All right, so working with some other programmer named Jasmine, I'm going to put the other talented programmer's name at the top, and then I would turn this in, and then as a grader, I would assign this both to myself and this other talented programmer. Oops, get rid of that. All right, so that's just some style issues associated with doing the class for me. Now, if you are a professional software programmer and you work with a group of other people doing software coding, your team is going to have rules for how your code should be structured. And the reason why teams do that is because for efficiency, if multiple people are writing software, it's a lot easier to look at someone else's software if it's formatted and structured visually the same way. It helps reduce the amount of time it takes to work with other people's code. So that's an important part. Style and commenting, although they're not integral to the algorithm, are an important part of doing software development and how we do software development together. Okay, let's look at individual components of this Hello World program that we just wrote then, and feel free to ask any questions about these if we need some clarification. But the first thing here's a program that I made beforehand. This is like a cooking program. I have made this wonderful pie, and I'm just going to pull it out all baked for you. This is a valid Hello World program, and there's a couple things that are present here. The first thing I want to draw your attention to is the fact that we have the keyword class there. The fact that we have a word class there means that we're defining the object. Later we can instantiate objects of a certain class, but we're creating an object by using the class keyword. And again, this is a fundamental building block of all Java programs. So in Python, we had a way of defining classes where we said def class, I think, if I'm remembering correctly. This is the same words, same context for the word, slightly different syntax. All right, so that's the main thing that we put in this file. Everything within this file, with the exception of the comment, occurs within the opening brace and the closing brace of this particular object. If we wanted to define a different object, we'd create another file and put it in our source directory, and then those two objects would know about each other, but they're each their own object. All right, the next thing to draw your attention to here is the methods in this class. So methods, we know, are also a part of classes. So if, let's see, so if this is the name of our class, and this is saying that we have defined a class, then this here is the name, oops, that was kind of ugly. This here is the name of a method. Let's see if I can get it. Third try is a charm. There. The third time is a charm. Blah, 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 blah. Main is the name of the single method that's present in this class. We can have many methods in a class that's consistent with other languages. In this case, we have one, and it is called main, and we have chosen that name. That name has special meaning, though, because we have to have a main function in order to start a Java program. All Java programs are started by indicating to the virtual machine which object you want to run. And when you indicate that object, the virtual machine looks for the main method in that object to launch the program. If you remember from our discussion of Python, the way we structured our Python programs is down at the bottom, we would have a call to main, a method, and then we would define a main method. That's because there's this echo of this idea of a main function being the place that we launch things from in many languages. In Java, it's hard-baked into the virtual machine. So the reason why we've got main there is because we need it in order to launch our program. It is also a method, though. It's a special method. Okay, so main method, that's our launching point for our Java program. We also have the body of our program. The body right now is pretty simple, but we're going to be able to extend it. The body of the program is everything that's within those outer blocks of the curly brackets. That's pretty easy to understand. The state, oh, sorry, I think I went too fast. Method call, go back a second. All right, method call. All right, so where is our method call? Let me go back one more, just skip one. Shoot. Sorry. Okay, so methods are part of the class. We have the main method. Great, there we go. All right, so the body of the program is everything within those bounding blocks. A method call. So main is a method. How do we call a method? Where is that happening? So right here, we have a method call. We're calling a method that's defined in another object. That method's name is printle. Typically, it's spoken as println. And there is one argument to this method, which is the string hello world. The argument follows in the parentheses there afterwards. So those parentheses designate all the arguments that are going to the println method. There is one argument in this case, and it's hello world. All right, strings. Strings in Java are delineated by double quotes only. In Python, you could use double quotes or single quotes. In Java, we only use double quotes. And we put any characters we want in between them. And Java now, by default, is Unicode aware. So you can type in international characters. You can type in some emoji. It gets a little wonky sometimes. But you can certainly do enye's and umlauts and Chinese and Korean characters and Arabic characters and things like that. It's also left-right aware and right-left aware, so you can type in other languages as well. In this case, we created a string literal by just typing it right into our code and putting the characters within the quotation marks. And that whole thing becomes one string object that becomes a parameter to our println method. So what did we do with that method? Well, what that method did is it printed to the console. All right, so this whole method right here ended up taking the string and writing it out, so providing some output along the way. And you saw that little window that was present in the Eclipse IDE that showed the output. That was the console window, but that's just showing us what the program would output in whatever context it was run. So the last thing we're going to do in the lecture today is I'm going to show you doing this outside of Eclipse so that you can see that, that tool chain working without the benefit of the IDE. And then I'll show you how the console isn't necessarily the same place every time. If you're writing things for an iPhone or for an Android phone, they don't have consoles in the same way. So because there's no like text window that you can write stuff to in a smartphone, you tend not to have consoles in phones. Okay, so our compile chain in Java looks something like this. Let me see if I can draw it for us. This is what's happening if you open the hood of Eclipse to understand how you're getting feedback from Eclipse of where you have errors and where you don't have errors along the way. And so what I want to do is sort of show what's happening. And then once we show what's happening, we're going to look at it on the command line to break it down. Why am I showing you this? Because again, it's important to have a correct mental model of what's happening so that when you have bugs, you know how the world is structured so you can identify how to fix it. The other reason why I'm showing you is to kind of give you some appreciation of all the work that Eclipse is doing for you. Because, let me turn on my old geezer voice. Back in the day, way back in the day, before there were great IDEs, you had to do all this on the command line, and it was horrible. And that's why we made IDEs, because it really sped up the process of writing code and made it a lot more palatable to write things and actually write code faster. So we want to just develop a little bit of appreciation for that. All right, so roughly what happens in the compile chain is you have some kind of editor over here. Our editor is the place where we write our source code, where we literally type in the text of our characters that's going to be compiled. And then our editor gets passed to the next stage, and the next stage is the compiler. Like a second grader is drawing this diagram, but that's okay. Maybe a kindergartner even. The compiler is a program that takes the source code text file that you wrote, and it's going to output it to bytecode. Bytecode is this intermediate representation that is platform independent. And this is notable because it has .class as an extension instead of what you have over here, which is .java as an extension. So usually we're working over here, and then eventually we get these independent programs here. In addition to the bytecode that you have compiled, you also can take in other .class or other, sorry, not class files actually, other bytecode that's usually in .jar files, and these are libraries. So libraries of other objects and methods that you might want to use. And so this will be a library. Together, these get fed into what we've already mentioned, which is the virtual machine. And then the virtual machine runs your programs, and then you have the happy user who gets to use the program as a result. So you see this on your computer maybe. Happy user, happy user. One thing to say about this virtual machine term. You may be familiar with the word virtual machine, the words virtual machine, used in the context of like web applications or web servers. There's a way in which virtual machine is used that's used to describe a simulated computer, an entire simulated computer. Like if you've ever used the VirtualBox software or VMware, or if you've ever bought a web server with some kind of online hosting company, one way in which virtual machine is used is a simulated computer on which you run a website, typically. That's not the way we're using it here. The way we're using it predates that understanding of virtual machine, and basically it is a simulated computer. It's a computer that's running this Java bytecode, and it's just its own program that's just running this bytecode over and over again. So the term, don't confuse the term virtual machine the way we're using it with virtual machine the way it's used in web software. Have you guys heard virtual machines used in the other context? Okay, so this is the tool chain, and so what I'm going to do now is I'm going to do this for you on the command line so that you can see that actually what's happening here. We just actually did that as our assessment, so we'll pause for a second. All right, so first of all, I've got my program here, and what I'm going to do is I'm going to go into the location on my hard drive where I've got that stored. All right, so I am now in a terminal. If you're not familiar with terminals, this is a way that you can work with your computer through text rather than through graphical user interfaces. So the first thing I'm going to do is I'm going to look and see where I am in my hard drive right now. I'm in the directory, from the root of the directory, it's called users, and then DJP3. You could look at this in the Finder as well, and what you would see in the Finder is a bunch of directories like these here. But I'm going to change directories, and I'm going to go deeper into my file hierarchy to a folder called Documents. And then within Documents, I have one called Class Resources. And then within that, I have a folder for this class. And then within that folder, I have the Workspace. And if I look and see what's there, I can see my Hello World program. I'm going to go into my Hello World program, which is now the same thing as what I have over here in Eclipse. I'm going to look around. There's my source folder. The bin folder that's present on my hard drive is being hidden by Eclipse. It's not showing that to me in my view. Go into my source folder, and I can see my package right here, edu. I go into edu, see the next level of my package, Westmont, right there. I go into Westmont, and there's my source code. So let me clean my screen up. There's my source code. If I want to look at my source code, I can write it out to the console here. So that's the contents of my file. It's the same as what's being shown in Eclipse. And what I would like to do is I would like to run that Java compile chain independently from the command line so that I can see how all these things connect to get together. So the compiler is called Java C. And so if I run Java C and I give it the input of the file that I want to compile, it will take that file, compile it to bytecode. If I had some errors, it would have not worked. Fortunately, there are no errors. I already cleaned it up in Eclipse. Now if I look, you can see I have that intermediate bytecode present. I have a hello world.class file. That's a system-independent file that I could send out to other people that they could run it as well. But now if I want to run it from the command line, I can actually run the Java virtual machine and pass it the hello world class, just the class name. And when I do that, it's going to look in the hello world. So I'm just going to give it Java hello world. That instruction says, hey, Java virtual machine, look for a file called hello world.class and run the main method that's present there. If I do that, I get an error because what did I do wrong? Could not find the main class hello world. No class definition found. Okay, let's see. Sure thought it was there. Get rid of it. Oh, okay. Small detail about the package name. I'm just going to get rid of the package for the time being. All right, compile it again. Now I run it. I get the output to the console. So notwithstanding what was going on there with the package, you can see that I can run this program from the command line, and the output goes to the console, and in this case it means it's output there on the command line itself. Now this means that this file, hello world.class, that just exists, and I can run that anywhere. Like I don't need Eclipse, and I don't need all that stuff. I can just run it from the command line, and that's very powerful because you don't need all the infrastructure of Eclipse in order to run a program. So if you wrote a bigger program in Java, you could package it up, and you could ship it to someone else, and they can run it as long as they have the Java virtual machine on their computer, which most computers do. They can run it without Eclipse. So just like any program you might write, you can send people that program, and they can run it without Eclipse. Tim? Well, let's see. So C++ is a little bit different because you can't, when you compile something, so the question is, do computers come with Python installed? How does this work with other languages? There's a very low-level language called machine code. And when you write a program in C, you compile your source code into bytecode, and that only works on one specific computer, model of chip, and operating system. So C, when you compile your code, you're compiling it for a specific operating system and a specific chip. And so if you want to run a C program on different architectures, people have to compile it themselves, or you have to download a version specifically for your architecture. So you'll download the Windows 386 version or the Mac PowerPC version or whatever architecture you've worked with. Someone has to do the work of compiling it for your specific architecture because the ones and zeros work on the chip level. What's happening in Java is that bytecode is being fed to the virtual machine, and that virtual machine has to be written for a specific architecture, but the bytecode doesn't. Python works like Java. Yes, every architecture of computer has its own virtual machine. And there are also different implementations of virtual machines made by different companies that work on different platforms as well. So there's not just one virtual machine. You can get a virtual machine from different organizations as well. Python works with like Java. There's not you have a Python virtual machine that runs the Python code on whatever machine you're on. So that was part of it. Does it work the same way with Python? The other part of it does, your question was, do computers come with Python installed? Increasingly, Python's a pretty standard thing to have included in out-of-the-box computers. I think Mac is shipping with Python now. I don't think Windows comes with Python automatically. I don't think that Windows or Mac come with Java automatically either, but it's really easy to get it and download it if you need to. I think that the usual, at least historically, what computers have done is they've only allowed the machine code to run on their computer. This idea of virtual machine is like a fairly new, we're talking like maybe 10 or 12 year new concept. And the way in which software is delivered with operating systems is evolving to support the new method of running programs as well. Okay. Okay, so that is us getting an appreciation of the Java compile chain. When we run Eclipse, so let me just go back to Eclipse here for a second. All that work is being done for us. So like if I make a change here, if I delete that and I save the file, immediately Eclipse is going through and it's sending it to the Java C program. So it's just constantly running Java C. And if Java C gives me any errors, Eclipse reads those errors and it translates it into the graphical user interface like here. Like right here, it's saying, hey, you need a package, so add that package. So it just reran the compiler again. And so now it's doing all that work for me in the background. So that's pretty helpful. All right. So as we think about that, we already made our Hello World program. We took some time to do our Hello World program. I want to, before we're done for today, what I would like to do is talk about two kinds of errors that we might have in our program. Also, just as a side note, what we're doing today is we're going through chapter 1 of our textbook. And so in terms of assessing our work through chapter 1, I'll be putting out a Techne assignment for chapter 1 shortly that will refer to some of these issues of compile time and runtime errors. You'll also need to read the book as well because it will cover things that we haven't had time to cover. So let's talk about two kinds of errors. One kind is a compile time error. We sometimes call this a syntax error. This is when we make mistakes in not following the rules of Java syntax. And it is the kind of error that can be discovered before your program is run. It can be detected by the compiler. So let me show you an example of that. Here in our Eclipse window, we currently have no errors. It looks like I have a spell check error here. If I hover over it, you can see that it doesn't think my name is spelled correctly, but that's incorrect. My name is spelled correctly. But I could have some kind of a compile error. So let's say, for example, that I didn't use the right, I forgot to put the N in this method name. I would get a compile time error from Eclipse. Now here's what is a way to use Eclipse powerfully. If Eclipse gives you a compile time error, it's going to underline the location in your file where it thinks the error occurs. Sometimes it'll get a little out of sync, and you can usually fix that up by saving your file, and it'll reset it. But what's powerful is that you can hover over this little light bulb, and it'll tell you what it thinks is wrong. You have to understand, you have to learn over time how to interpret these errors, but if you read that, it says, the method priln string is undefined for the type print string. All right, we might not know everything about what print string is. We might not know about that type, but we do know what a method is. And by saying that a method is undefined, what we can understand is from the perspective of the compiler, is the compiler saying, hey, I've never heard of this method called priln. And you're like, what do you mean? You've heard of println before? No, I've never heard of priln. You've heard of println? I just saw it in the notes. I've never heard of priln. And what you've got to identify is that what you thought you typed is not what you actually typed. And if you read that, you can see feedback from Eclipse telling you that something is wrong, and in particular that you typed something out wrong. So that's an example of a compile time error, something that Eclipse can recognize right away, something that can recognize before you run the program. But a second type of error is much more pernicious, and this is a runtime error or a logic error. This is when you have written completely valid Java code, but for whatever reason, it doesn't do what you wanted it to do. So your program will run, but it's not going to have the effect of what you wanted it to do. So what would that be like? Well, that would be like, instead of saying hello world again, what if I actually said hell word? And what I really wanted to do was say hello world. Well, there's no compile time errors here. There's nothing wrong about the syntax. I can run this, and the console will print out hell word. But that's not what I want. That's a logic error. And so I don't get to see that that's an error until I run the program, until I see the effect of it. And then I can say, oh, hey, I made an error in my text. I'm going to go back and change it. Hello, word. Up. So then I can go back and fix it. So in your mind, you can think about errors as being in these two different categories. You can have a logic error and you can have a syntax error. And they happen at different points in the chain. Now, there's one special kind of runtime error, which is called an exception. And an exception is a runtime error because it's something that the compiler can't recognize at the time of writing your program that has gone wrong, but which is going to cause your program to crash when you actually run it. And that's because not only have you asked your program to do something which is syntactically okay, but in the time of running it, you're actually going to get an undefined or an error of some kind. So let me give you an example of that. One thing that we can do in our print line is we don't just have to use strings. We can do a math formula in there if we want. We can say print 3 plus 4, and if we decide to run that, we will get the output that we expect, which is 7 for the time being. But not every math formula that you might type in is necessarily well defined. So we might, for example, say 1 divided by 2. We'll use floating point numbers, so we'll say 1.0 divided by 2.0. And if we run that, we'll get 0.5. That's pretty good. So far, so good. But what if we decide to divide 1 by 0? That's syntactically okay, but if we actually try and run that, we're going to get a problem because 1 divided by 0 is something that we can't handle. Take it back. Infinity. Bad example. Darn it. There we go. So floating point numbers actually have a representation for infinity. Integer numbers do not. So if we make space for here, what you can see is something happened. It was a runtime error. It caused my program to crash. You can see that line 11 got run. It output a 7. Line 12 got run. It output 0.5. When it came time to run line 13, it tried to run it, and we threw an exception. And so if you look at the crash for that, you have to be a little bit patient, but if you read it, there's a lot of information there. It says there was an exception in thread main. I don't know exactly what that means necessarily, but you can see there's an explanation after the colon. It says division by 0. Oh, so now you kind of know what you're looking for. And then furthermore, after that, it says, here's where it's located. In the blue there, it says hello world.java, line 13. So if you do get an exception, if you take a moment to just pause and look and see what the output to your console was, you actually are given a lot of information about where to go to try and find that error along the way. So I read that, I go to line 13, I say there's a division by 0 error, what in the world's going on? Oh, there is a division by 0. What I meant was to do 1 divided by 10 maybe. And then this is probably going to be 0 because we're doing integer division. There we go. So 7.5 and 0. So we got out of our runtime error two kinds of runtime errors, one that is causes an exception and one that is just a logic error. Okay, so in summary, what have we covered today? We've talked about the way that computers consist of hardware and software. The hardware is the physical material stuff that we have that we can work with, the keyboard, the screen, the CPU. We have software. That's primarily what this course is about. This course is primarily about writing the software. That software gets stored in a file as a text file. And those two things work together in order to run a program. The software is compiled by the Java-C compiler. It is stored as a file on your secondary storage. Your virtual machine runs in the CPU, and it brings in the bytecode from your file, and it interprets that bytecode, and it moves things along the bus from the screen to the keyboard, from the keyboard to the screen to the internet, so that that virtual machine is working with the hardware to create some effect. The software that we're writing, we're going to write with an editor. I say the term editor because I just generically mean anything that manipulates text. You could write code in Microsoft Word if you wanted to. It's not very well suited for it, but you could. Eclipse has its own editor in it that helps us and gives us a lot of tool support for writing well-formed code. So software is written in an editor, but then it's compiled to make it something that the computer itself can run. In Java, it's bytecode. And that bytecode is run on a machine-specific, an architecture-specific virtual machine. So that's what we've got for today. Any questions from online? Any questions from in here? Yeah, what do you got? Statements from the Peanut Gallery? Oh, yeah, thank you. Yeah, online, the person who invented Java was at Sun. That's absolutely correct. And then Oracle bought Sun. Yep, that's right. Yep, it's all flashing back in. Oh, yeah, so the person online immediately saw what my error was and then helped me out. Thank you. Oh, Dr. Iba. Thank you, Dr. Iba. I need to get you on a more direct connection straight to my brain so that I can identify what's happening. Anyone else? Okay, then what we're going to do is we're going to wrap up for today. Thanks for your attention. I appreciate the comments. We're going to start moving into our next chapter. Be looking on Canvas for a little bit more structure for what's coming up. And you've got a Hello World assignment due, and you're going to have a technique for chapter 1 that's going to be on Canvas shortly. All right, so to all of our people out in the internet world, it's been good to have you with us. We are shutting down. So long. Goodbye. Good night.